In this session, I would like to talk about hardware components related to your instruction execution. Before going to that, first of all, we start with this idea. So, I am using 5 stages of instruction execution. Already I told you, whenever you divide the instruction execution into some stages, then definitely you get an advantage of pipelining, correct? We will see that in pipelining. Why you get advantage? If you have multiple stages in the instruction execution. Now, here I am assuming that, let's say I have 5 stages in instruction execution. The first stage is fetching the instruction. In the second stage, what we do is we understand the instruction. Okay, so that is called decoding. So we decode the instruction. Whenever I decode the instruction, I understand what is that instruction. Is it add, otherwise subtract, otherwise maybe shift, otherwise load, store, whatever. So by understanding the bits in this instruction register or instruction, we can understand whether what is the desired operation. Okay, after that what we do is, so we read the registers. Example, the instruction is add R1, R2, R3 something. Then here in this stage I am going to understand that this is add instruction, and I will be reading R2 comma R3 register values into some temporary registers. Okay, so in the third stage what I do is I will be doing the required arithmetic. Since it is an arithmetic instruction like addition, then already that registers R2 comma R3 values are read, right? So that values I will be adding in the ALU. We will see the hardware components, don't worry. So at this moment just understand that in ALU stage we will be adding the registers. After that we have to store the result back to R1, right? So that we will be doing in this stage, fifth stage. But in the fourth stage what I do is I do memory access. Example, if the instruction is load R1 and 1000 of R2, something like this, then what I am going to do is in this memory access stage I will be accessing the memory part, main memory. Okay, let me show how this load R1 and 1000 of R2 will be executed, okay, with respect to various stages. In the first stage we will be fetching this instruction and we will be keeping it in instruction register, might be. Okay, in that way you can understand. So after fetch phase, what is going to happen is your instruction is in instruction register. After that, in this stage, second stage, we will be reading the registers, of course, plus we will be doing the decoding also. Okay, decode. So since we have pattern here, instruction pattern, by seeing that instruction pattern we can understand what kind of instruction it is. Okay, so such a way we have to design the decoder. Okay, assume that let's say you have a decent decoder who is understanding that now current instruction is load. Then what it will do is it will read register R2 into source registers. That means in the second stage we understand the instruction and we read the registers which are required. Okay, here especially that is R2. Now in the third stage what we do is, so we will be doing arithmetic. Sir, why for load instruction arithmetic is required, especially for this kind of instruction? So you know the meaning of this one, right? Load R1 1000 of R2, that means 1000 plus content of R2. Already we have register R2 value, add them 1000 plus R2, and this addition is nothing but done here ALU. Okay, so that means here also if for load instruction also ALU is required, correct? So 1000 plus R2 will be calculated. Once value is calculated, then we will be loading the value at 1000 plus R2 into R1. So there will be main memory. In that main memory there is a location called 1000 plus R2. Let us assume that content of R2 is something 50. Then 1000 plus R2 will become 1050. We will go to 1050 and we will take that value, we will transfer that data, okay, into a temporary register here. That is called memory access. Once you do memory access, once you get the data, in the next stage what we are going to do is storing the result into destination register. So now you have data which has to be stored into R1, that we will do here. Okay, now I will tell you how we are planning again. First we fetch here and we understand the instruction here and we read the required registers values into in this stage. After that we will do arithmetic here in the ALU stage. After that here we do memory access if and all if it is there. In the last stage we will be doing what? Storing the result back into registers. Okay, So in that way we can systematically plan. Now we'll try to understand store. Okay, example, let's say store R1 in the 100 of R2. Assume that content of R2 is 50. So what is going to happen? I mean, if I execute this instruction, and in which stage what work is going on, we will see. First step, instruction register. This is, let's say, instruction register. The first step is fetching. Whenever I fetch the data, then instruction, that instruction, this store R1 100 R2 will come here. Okay, yeah. In the second step, we decode it and we understand that it is store instruction. Then the necessary signals we generate, we will see that in control circuit generator. Okay, that means we will be designing control circuit. That circuit is going to generate appropriate signals. Because of that, automatically remaining tasks will be done. Forget about that. Okay, sir. So how this control circuit will be designed so that automatically this 100 plus R2 will be added, everything we will see later. Here our idea is how this, I mean, execution can be done in 5 stages. I am explaining first. So what is my expectation is, in the first step, I am just teaching you what is our expectation. I am not teaching you at this moment why it is happening. We will see that later, that for that we need a circuit, right? So the circuit design part we will see later. At this moment we are just understanding what we want. So in the first level, in the fetch stage, we will be fetching the instruction. In the second stage, we will be decoding that instruction and understanding that it is stored. Then appropriately we will be doing the remaining stuff. That remaining stuff is like this. So in the decode phase, we will be reading what? R1 comma R2. So value of R1, let us assume that, let's say, value of R1 is something like 50 and value of R2 is 100. We will be reading in this phase. Okay, so 50 and 100. In the next stage, what we will be doing is ALU. So what is ALU operation here is this absolute address, immediate value 100 and content of R2 which already we read, which is 100. That 100 plus 100 will be added in this ALU phase, right? That means, so in this arithmetic phase, 200, right? You get here 200 ALU. So after that, memory access. In the memory access phase, what we will be doing is, so we will be going to main memory, especially to 200th location, right? 200 memory address, where we will be writing this data 50. So that will be done in memory access stage. After that, in the 5th stage, we don't have any work. If you have to store anything into registers, then we will be doing into this 5th stage. So that's why finally fetch, source decoding and ALU and memory access. These 4 stages are essential here, like, you know, they have significant work. But in the 5th stage, there is no work. We will be keeping quiet. Already I explained you, right? So this is about the 5-stage model we will be using. What people realized is, if the instruction execution is divided into 5 stages, then most probably, so it will be good, right? So now we will see the hardware components, like how to design our hardware such a way that, you know, we can carry out all these tasks. Okay, so we will see that. First of all, we start with simple idea, that is how these registers can be accessed. What is the model, right? Assume that, let's say, you have some registers, CPU register, which are 32 or 64, whatever. Let us imagine that that is a file. Okay, so this is a register file. So in this register file, if I specify the address, we have to design it such a way that whenever through these address lines, I will be using 3 address lines, 1, 2, 3. So these 2 address lines generally for, you know, accessing the registers, that means, you know, taking the data out, and one more address line, this is, let's say, address C, that is for giving the data. Try to understand. So we have to design our system such a way that it should have collection of registers. That means we have to implement a circuit such a way that that should have some 32 or 64 registers. Let's call it as register file. Okay, so here each this row is nothing but one register. Now you have to design it such a way that, so you, whenever address lines are specified, the correct, otherwise the desired register should be enabled, that should be able to access. Okay, we should be able to access. Now second thing, sir, why this 1, 2, 3 lines? So our RISC design is such a way that our instructions are such a way that we need most probably 3 registers, right? So you see example add R1, R2, R3. In each instruction, especially in this kind of arithmetic instruction, we will be using 3 registers, right? 2 for taking the data and 1 for giving the data, right? Similarly, load R1 100 of R2. Here of course only at most 2 registers are required, correct? Now similarly store R1 something 100 of R2. If you do this, then here one is for storing the data, one register, one is for taking the data. Similarly in load, one is for this one, see, we will be taking the data from 100 plus R2 and we will be storing it in R1, correct? So here also we require one register to store and one register to get the data. But of course here if you see, store R1 and 100 of R2, we need 2 register to take the data, correct? But we are not giving the data back, correct? So in that way if you see, we need 2 register to take the input and we need at most 1 register to send the data back, right? Such a way we have to design our register system. Okay. Now example, see, this is a model we will be using. Assume that let's say these are all registers. So to add address A, address B, whenever I specify, how to understand this I am telling. Specify address A, address B here, whenever I specify like that, then data automatically comes from these cables. Okay, this is not a single line. Okay, it's not a 1-bit cable. So this is a line from which you will be getting all the data of one register. Example, register size 32 bits, you will be getting some 32 bits here. Okay, similarly another register also, let's say the size is 32 bits, you will be getting 32 such bits, right? Now I'll explain with one example. Whenever you write add R1, R2, R3, so what is going to happen I will tell you. Assume that let's say somehow your control circuit should be is designed such a way that this R2 is automatically connected here, R3 is connected here. So what is happening? Content of R2 is specified as address A, address B, and content of R3 is specified as address A. Then automatically this register R2, register R3 will be selected. Their data will be taken here. You will get here. Right. Now, sir, what about this one? I connect it here. So that whenever R1's address is specified, then that register, one of the register, example this is R1, that will be ready to take the data, right? Sir, how to give the data then? See, through this line, okay? So this line is specially designed for giving the data. Example, you have some value 50, okay? You want to give that value here, then simply connect like this. Of course, but that is not our purpose. We will be doing what? We will be storing the result after adding R2 value and R3 value. How to get R2's value and R3's value? Now I show. Now by this time you clearly understand this. If you really want to get R2 value, R3 value, specify R2 address here and R3's address here. Okay, when you do that, then what is going to happen here? You have to specify address of R2, address of R3. Then the data of R2, data of R3 comes from here. Now, really you want to implement add R1, R2, R3, what you have to do, you know, you have to connect R2 comma R3 here and we have to take the data. See, data comes from here. Then take an ALU, okay, so this is let's say your ALU and we connect like this, one of the input to here, one of the input here. Assume that this ALU is designed such a way that it can take some 32-bit inputs and it is going to add them. Sir, you did not teach us how to do addition, already I taught you, right? So in arithmetic part, already we have covered that part. So how to do addition of 32-bit numbers we have seen, right? So using such circuit, so here this box should be replaced by that adder circuit. Then you get the result. See here, some 32-bit or 33-bit value you are getting. Assume that let's say 32-bit data you are getting back. Then what you do is specify R3 here and connect this line here. So what is going to happen finally? R2, R3, the content will be taken here and they will be added here. Let's say it is added. Then the result is taken here and that is connected here. And if you connect R3 here, So whenever you enable this R3, that means whenever you specify R3's address here, automatically the right, sorry, it is R1, right? It is R1. So whenever you specify address of R1, since you connected this cable here, the result will be stored in the appropriate register. In that way, so address A, address B, address C can be used. Such a way we can design it. Okay. So that this is very important circuit we will be using in our hardware devices. Okay. So remember this component, we will be using this one. Already I told you, I am going to teach you hardware components related to execution of any instruction, correct? So we will be using this hardware component very regularly, just remember it. Now we will revisit that example. If you see, what is the difference you are seeing here? There is one multiplexer, right? So why this multiplexer? And you just focus here, immediate value, correct? So there are some instructions which doesn't require data from the register, right? So they require data from immediate value. That means, from the instruction itself, correct? Example, you have this kind of instruction, add maybe R1 and R2 and hash. This hash is just for our imagination, correct? So there will be one machine code related to this one. So that differentiates add R1, R2, R3 and add R1, R2 hash 100. Assume that, let's say, your processor can understand the difference between this one and that one. Okay, such a way we have to plan our machine instruction patterns. At this moment, assume that, let's say, this is one of the operand is given as immediate operand, correct? So how to execute it? The previous circuit will not work because there was no chance of taking the immediate value directly, correct? So that circuit was focusing on this kind of instructions, add R1, R2, R3. That was working fine for this one. Now if I add this extra component, this one multiplexer, then you can execute this kind of instructions. Let's try to understand that. Okay, so how you see, somehow, so you give R1 here, okay, sorry, R2 here, okay. So whenever I specify address of R2 here, then A will be, the data of A will come from here. Now such a way we have to design the circuit, I am telling. So second thing, so somehow you give 100 here, immediate value. Then what is going to happen? 100 will flow like this. Sir, but it is why multiplexer? I will tell you. So this circuit is going to support this kind of instructions and this kind of instruction. What is another one? Add R1, R2, R3. If you want to have this kind of instruction execution, then in the place of this immediate value, this line should be enabled, okay, and R3 should be connected here. Understand? Now by connecting R2, R3 here, automatically what happens? R2 comes here and R3 will struck here. If you select the proper line in these two, that is the job of multiplexer. So there will be one control line, okay, one line, control line, okay. So by properly adjusting this control line, we will be able to select either this one or this one. Now whenever the instruction is add R1, R2, R3, then we have to select this one, and whenever it is add R1, R2 hash 100, then this immediate value to be selected. Such a way this control line should be enabled, right, properly. We will see how to enable. Example, see, this is 0, this is 1. So what do you want exactly at this moment? This one, right? 1. That means you want to have input from this 1. So that's why you just write control line 1. That means enable the signal. We will see that part later, right? So how this control line will be appropriately enabled? Whose job is that? Control circuit. We will be designing that. At this moment, assume that, let's say, we are just designing the circuit part, okay? But how to appropriately enable, that is job of another machine, I can say, another circuit, that is called control circuit. We have to design it. I will teach you how to design. So all that questions will go to again control circuit, okay. Now at this moment, don't worry about that. So finally this machine or this circuit, this small circuit is able to add R1, R2, I mean execute add instruction of this model and this model, yes or no? But appropriately the signal should be enabled, right? That means appropriately that line should be passed. That will be taken care by control circuit, just remember it. Now finally you understood this model, right? Now what happens really, if you connect R2 here, then automatically data comes here. Let's see that seriously now. Sir, what about this one for add B? Give don't give anything. Don't give anything. Then maybe whatever the previous data, whatever it is having, maybe that will be enabled. Doesn't matter. You don't get any wrong. Why? Because we are not supplying any valid information here, right? Sir, what if we take some wrong information? You know one thing, right? Whenever you don't connect something, like example, let's say you have some cable. In that cable, if you don't connect anything, then what happens? It will have some old value, right? In digital electronics, you already learned. So this will have some old content, correct? So that means example, in the previous instruction, this add B, address B was connected to something R4, then that R4 register will be enabled here. Sir, then you get wrong, right? R4 was not our intention. Yes, not a problem. Because if really you execute the things properly, what we are going to do is, we will not be specifying any valid address here, but only we are giving here a valid address here R2. Slowly R2 comes. I am showing you how to execute add R1 R2 hash 100 using the circuit. So R2 slowly comes here, perfect. Then now 100 we give here, and the control signal will enable properly, so that we give one signal here. Whenever I give one signal here, then this line will be selected, then 100 will pass through this cable, then 100 plus R2 will be added if you take adder here. Okay, I am assuming that appropriate. Sir, what is ALU, sir? ALU is nothing but set of devices. I can say set of circuits. Adder circuit, subtract, maybe if and all, if it is there, then subtractor circuit, otherwise maybe comparator, okay, division circuit, multiplication circuit, shift circuit, everything. The collection of all the arithmetic logic unit, that's it, you know that, right? So it will have lot of circuits. So the right one should be enabled. Sir, who will enable that? Sir, how do we know that? Otherwise, how processor knows that now at this moment adder should be enabled? Don't worry. So that will be done by again control circuit. So this ALU will have some control lines like this. Okay. If you want addition, this signal should be enabled. That means this line should be enabled. If you want subtraction, this one. If you want shift, this one. If you want multiplication, this one. Such a way there will be switches, I can say. Otherwise I can say some cables. So appropriate cable if you select, then automatically appropriate circuit will be enabled, and that will do the desired task. Such a way we can plan it. So that we don't discuss here. That's you have to learn it in digital electronics. Okay. So at this moment, assume that because of our operation which is add, did you remember I said decoding? Decoding is nothing but understanding that it is addition, and appropriate adder circuit should be enabled here. That will be done by your control circuit. I will teach that. Okay. Now at this moment, assume that let's say we have adder that is going to work. Apply your brain now. Okay. Since we know that it is addition, then take adder and connect them, this R2 and 100 to adder, so that R2 plus 100 will be added. So where it has to be stored, we have to store that R2 plus 100 into R1. For that, we have to connect this add C to R1. Okay. So this is what should happen, right? For that we have to design the circuit. Finally, at least we have a circuit which is going to do whatever we want. The only thing is it should be controlled properly, right? That's why control unit. We will be designing that control unit. It's not a big deal. So finally, this is one important circuit we need to evaluate, otherwise execute some instructions. Now we'll slowly extend it. Okay. Now to execute load instruction, store instruction, and add instruction, everything, what kind of complete circuitry you require, if you want to know, then this will be the idea. Okay. So now here this circuit, otherwise this I can say this also known as data path. This is also known as data path. So this I can say, forget about the data path keyword, you will slowly understand why it is data path, because your data is traveling from here to like this, in that way. Okay. That's why it is called data path. So you have circuits, through this data is going to pass. That's why it's a data path. Apart from that, it's first of all a circuit. So this circuit is enough to execute any instruction. Okay. Now we'll see the functionality of this circuit. Sir, why are you teaching us circuit, sir? So in the gate exam they don't ask any question related to a particular circuit, yes, but if you have idea like how your typical instructions are getting executed, then you get confidence. Otherwise, if I don't teach you the circuit part, then what happens is you will lose confidence. That means your brain says that you don't know actually what happens inside the computer, then you can't answer easy questions, right? Even easy questions, that's a problem because of lack of confidence. When you understand the real things, like complete things, like how computer executes your instructions, everything, that boosts up your confidence. Because of that, easily we can solve questions. Okay, now that's why let me teach you this circuit part. So using this we can execute end to end, like load, store, everything can be executed using that. We will see that. So let me show this component here. First of all, this is set of registers, right? So it can register file, also known as register file. Can you locate this component here somewhere? Yes, you can locate it. Where is that? Register file here. These are all set of registers. Now, so there should be two address lines for input, one for output. That means, sorry, two for output, one for input. To take the input, one address line. To take the data inside the registers, one address line. To take the data out, to bring the data out, two address lines, we know that. But appropriately they should be connected. That will be done by your control circuit at this moment. Let's say we do manually, like we'll give appropriate, I mean using our human brain, our brain, we will be connecting appropriate registers. Okay, slowly you will get the experience. Don't try to understand everything at a time, right? So here now I teach you how the circuit works slowly. Now first thing, this is nothing but this one, see, register file. Second thing, you have multiplexer, here we have multiplexer, you have ALU, we have ALU. Sir, but we have this RA and RB. I did not understand why these two registers. I will tell you. So, because we are going to do the things with pipelining. Pipelining is one important aspect. Otherwise, using that technology, we will be doing parallel execution of instructions. For that, your data, I mean, your machine should be designed in a staged way. Like that means, like your instruction should be executed as multiple stages. Already explained, right? So when you are doing the work in stages, sometimes you have to hold the data and you have to pass the data to the next stages. Agree? That's why. So this intermediate registers are going to help you. So what we will be doing is we will be imagining this circuit as stages. Actually, so this stage to here, I will slowly you will understand. Okay, don't worry. So here to here, this circuit is going to do stage 2 functionality. Now this circuit here to here, okay, forget about these registers. If I forget these registers, is it not a register file which is connected to ALU? See, register file is connected to ALU. Forget about temporary registers. That temporary registers is just like buffers. They will hold your temporary, otherwise intermediate data. Okay. So that will be important for us in pipelining. At this moment, let me design the circuit like that. Okay, slowly you will understand the purpose. Now see, register files and ALU, correct, multiplexer. So this component is this, right? So apart from this component, we will be using some extra component. What is that? I will explain you. So here finally you will be doing ALU, right? Once you do ALU, then again we will be holding the data in temporary register. That register is becoming an input for the next stage. So you see here, first of all we'll see the stages. So this is stage 2. Now whatever we do with this circuit is stage 3 functionality. You don't understand at this moment because you don't clearly imagine what is stage 2, what is stage 3, correct? So don't worry, I will take one instruction like load or store and I explain you the circuit's functionality. At that time you map that, oh, this is stage 3's functionality, automatically you learn it. Okay, so this is at this moment stage 4 functionality, and see, here to here and here to here stage 5 functionality. We do stage 5 functionality here and here. Okay, to understand that clearly we take one example. Okay, let us take first addition part. Same thing. So we learned already how to do addition, right? Let us use that one. Add R1, R2. Let us use immediate address. Whenever you have add R1, R2, immediate address 100, what is going to happen is first step. So here Sir, you did not show us stage number 1. What is stage number 1? That is fetch stage, right? So here fetch stage is different. That means, so this circuit is not about fetching the instruction. That will be done by another circuit that I am not discussing at this moment. Okay, that is little bit complicated. So we are learning the circuit and the data path which is related to stage 2, stage 3, stage 4, stage 5. In the stage 1, what we do? Forget about the circuit. What is your expectation from stage number 1? In the stage number 1, this instruction should be fetched, correct? So after that, so remaining thing right? So we have to, in the stage number 2, in the stage number 1, this instruction should be fetched. Yes, now we have this instruction. So what is going to happen in the second stage? In the second stage, this register 1, register 2, this value will be appropriately connected. That will be done by control circuit. We will see that later, right? So at this moment, let me connect properly. You tell me, we have two address lines, correct? Out of them, how many are useful? Because one of them is immediate value, right? So immediate value we provide here. That means your control circuit should work. The circuit should work such a way that immediate value in this point, this 100 should be connected. Okay. So second thing, R1, R2, 100. This R2 should be connected here. We know that, correct? Yes. Now this R1 address will be connected here. So that now this register file is ready to take data into R1, and at the same time it is ready to give data of R2 through this cable, right? So finally, can I say like this? R2 is coming here. Sir, what is coming here? Some dummy data, however we are not taking it. So assume that your multiplexer is properly selected by your control circuit so that this this 100 is passed. That's why it is called data path, right? Now see, your data is transferred. Finally, you remember one thing, instruction execution is almost like, so moving the data, right? You can easily observe. What are we doing? Just we are moving the data almost from here to there, there to here, that's it. So that's why mostly I can say this is, your circuit is nothing but data path. Now 100 will pass like this, correct? So 100 plus this R2's content will be added. Finally, here 100 plus R2 will be done, right? 100 plus content of R2, whatever, will be added here. Then that will come into a temporary register. The output will be taking into a temporary register called RZ. Now can I say one thing? So far what happened? Up to stage 3 is done. That's why it is called stage 3. In the stage 3, generally what we do? Arithmetic. That's why we are doing arithmetic in the stage 3. So this circuit will be related to stage 3. Now once you get the output, that we will be storing in RZ. So that will be supplied to, this multiplexer. Okay. Now that is the beginning of stage 4. You tell me what should happen, sir. Why this multiplexer? Here in this example we directly connected, right? The ALU's result should be directly connected to register. Why are you using multiplexer? Because already I told you, we need a circuit which can do addition, load, store, everything. To do all that stuff, this multiplexer is required. I will tell you the purpose of this multiplexer clearly. At this moment you tell me, what do you want? Sir, I want to store this result. I don't even want temporary register, sir. Directly I want to connect here to here. Then only addition will be done by your circuit. But to do load and store, that method will not work, right? So that's why, so what is going to happen is, here the result, that RZ will be connected to the multiplexer. So that multiplexer is connected to memory. See here, if you see the cable, we will be connecting it to memory data, and this is actually return address. Return address. I will teach you. So from where return address comes, I will teach you from where memory data comes. These two cables separate, I mean different. Okay, different story. Don't worry about them at this moment. I will explain that. For this instruction, assume that your control circuit properly enabling the cable, so that means there will be two control signals. Because of these two control signals, assume that, let's say, this channel is selected in multiplexer. If this channel is selected, what happens? The ALU data, whatever the computation is done, that addition result will come here. Then it will pass through this multiplexer. It will come to RY. Then this RY's data will be taken back to the register file. Because already we enabled the right register. You see, since this address is connected to R1, so whenever this data comes, that will definitely go to R1's register, so that data will be stored in R1, right? Now, Sir, what if that register file is not ready at that time to take the data? So for that, who should be ready at what time will be decided by your control circuit. Okay, so it's a big thing. We will see that slowly. Okay, assume that really register file at that time was ready, and this address whenever we specified, then that corresponding register was enabled and that was ready to take the data. Then when data comes, it will take it, right? Such a way we can design a circuit, right? It's transferring from one register to another register, right? So finally, see, properly if you generate the signals, like, so we can say like this: in the first clock tick this should be done, in the second clock tick this should be done, in the third clock tick this should be done, in the fourth clock tick this should be done. In that way, if you systematically plan your circuits, okay, then definitely the desired task will be done, right? So this circuit really helps you in executing this add R1 R2 100. Only thing is, these are all passive devices, they are ready to do the work, but appropriately we have to assign the jobs. So example, let's say this ALU should do addition only when the data is available in these lines, correct? But it should not do addition before data comes into this RA and RB, understand? So for that there should be timing. So timing will be generated by again control circuit. Your control circuit will give the timing to these circuits, don't worry. These are all passive devices. It's like slaves for us. We have to appropriately select them to work. Okay, we will see that part slowly. Now we will see how this load instruction will be executed. Okay, load, let's say R1, whether this machine or circuit will help us in executing load R1 100 of R2. Okay, let us try. So what we do is, I want to use this device or this circuit and I would like to do this operation. For that, what I do is, I will tell you. Finally, the destination is R1. The content at 100 plus R2, there is a main memory. In that main memory, so this is, let's say, 100 plus R2 memory location. 100 plus R2. There is a data called X. That X should come to R1. We have to pass that X into R1. That is what the meaning of this instruction. How this instruction will be executed, we will see. In the first step, assume that already fetching step is done. Step number 1 is done, or stage number 1's work is done. Now we are seeing this circuit is only partial circuit, which is doing the functionality of stage 2, stage 3, stage 4, stage 5. We will see in the stage 2. So your control circuit, and I am missing one part. What is that? Control circuit. Your control circuit will decode this instruction and it will understand that it is load, and appropriately it will connect. Otherwise, appropriately this circuit will be used by this control unit. Okay, so we will see that. So this control unit will connect like this, R1 here. Okay, so there is the address line, right? Here R1 will be connected, so that now in the register file R1 register is ready to take the data. Only thing is, data should come, right? Now second thing, 100 plus R2, we have to take 100 here, right? Same thing. So we can do one thing here, we can pass, your control circuit will pass 100 here. Now your control circuit will pass, R2 here, right? That means this this line, input line should be connected to R2. Now this is anything, we don't bother. So that what happens, you see, now R2 registers content will come here, and here some content will come which is not ours, don't worry, maybe wrong content, doesn't matter, because we did not give a valid address here. Some invalid address will be already existing, that will work, and that will give some data here, junk data I can say. In the next stage what happens, we'll see. Once data comes, then see, slowly it will flow like this, correct? Now R2 data will come here. Slowly this wrong data will come here and it will stuck at multiplexer. So for multiplexer there is a control selection, right? Now here this control circuit will give right signal such a way that this time this cable will be selected. Such a way we have to plan, then only it will work properly, otherwise you get wrong answer. So 100 will pass like this. So now here your control unit should generate a proper signal so that adder will be selected here. So 100 plus R2 will be done here, so that result will come like this, 100 plus R2, correct? Now that will be stored here. then recall, it is load, right? Now 100 plus R2. Now this C multiplexer here, are you going to store 100 plus R2 into register file? No. That means here this multiplexer should work properly, so that data, this 100 plus R2 should not go inside the multiplexer. Then which one should go, sir? I will tell you. See the cable, that 100 plus R2 is also connected to memory address. Okay, that means here what happens, I am missing some part of the circuit, that's why you are not understanding, you might not understand clearly. So remember one thing, here there will be a processor memory interface. Processor memory interface, what is the work of that processor memory interface? I will tell you. In this interface, so it is ready to take always memory address. Whenever you give memory address to that memory interface, then that is going to give the data inside that memory address. Okay, since we are connecting this cable to that memory interface, then what are we providing to that memory interface? One memory address. What is that at this moment? 100 plus R2. So 100 plus R2 will be taken by that memory interface, which I did not show in the circuit, right? So remember one thing, your computer is very complex, right, and complicated. You can't understand everything at a time, that would not be good. So don't you expect from me that I write complete circuit, complete computer circuit, and if I explain, then you will be messed up, right? That's why I don't do that. Only important things I'm teaching you. So finally what happens is, so here the data which is 100 plus R2, right, 100 plus R2 comes like this. So since this memory address is connected to this memory interface, that 100 plus R2 will be taken by this interface and it will give the data at X. So slowly that interface will give you X here. That X will come like this. See the memory data cable. So finally assume that, let's say that interface is going to give us memory data through this cable. So that, so slowly it will come like this. Now multiplexer is ready with data here, data here, data here, correct? Which one will be selected? That depends on the instruction. Your control circuit understands that it is a load instruction and data is going to come from the memory. So, and especially the valid data is now memory data, correct? So that's why this cable is appropriate for load instruction. So sir, how that control unit to understand that? We have to design the circuit such a way that whenever it sees load instruction, so at right time this cable should be, this multiplexer should be enabled. Okay, don't worry, we can do that, it's not a big deal. Assume that, let's say here there are some control signals. Finally the job of controls unit is deciding the appropriate cables. For that there will be some control signals, right? So by properly tuning these control signals, the right line can be selected. It's not a big deal, we can automate it, not a problem. That is what the job of control unit. We will see how to design control unit. For that we have lot of techniques, hardwired technique. Second one, micro instruction model. We will see that because that is very important. So now here at this moment, assume that, let's say that is granted. So automatically this cable will be selected. So now data comes like this. That means the memory data will come to RY. In the next stage, so by that time, first of all, initially it will be stored here. In the next clock cycle might be, so in the stage 5, the data will be stored back to this register. At that time, your control circuit should enable this address line with R1. Understand? Yes, it's not a big deal for your control circuit, right? So finally, yes, load R1 100 of R2 can be executed using this circuit if you appropriately enable the control signals, right? Similarly, we can show for store and other stuff also. I will teach that.